Hey, welcome back to Chapter 5, Chemical Quantities and Reactions. This is Section 5.3, and we're going to be talking about chemical reactions and equations. And so in this section, what we're going to do is we're going to take what we've learned about the molar masses and the molar relationships, and we're going to look at the ratios of how those things react actually in real life as chemical equations. So a chemical change is when a substance is converted into one or more substances that are completely different from the original, and so they would have different properties and different formulae. And so sometimes in a reaction you see this coming off as bubbles where a gas is given off, like carbon dioxide or oxygen. It could change colors. It could precipitate and produce a solid of some type. And so in the case of this fork over here, this is silver, and they're showing you that it has tarnished. And so that is actually a chemical change where you convert silver to silver oxide. So there are visible evidences of a chemical reaction. If they change in color, if they form bubbles, if they form a precipitate, or if they produce heat, or if they get cold during the course of that reaction. So that's an evidence of that chemical reaction. Which of the following represents a chemical change? Put this on hold for a minute and see if you can figure out which would be a chemical change. Remember, look back at the definition of what a chemical change is, okay? And then come back and we'll see how you did. Well, burning a candle, are you converting that to something other than what it was? Yes, you are. You are giving off smoke, which tells you that you're giving off something. Is ice melting? No, ice melting is a physical change, if you remember from an earlier chapter. A physical change is where it's still water, it's just in a different phase. Toast burning is a chemical change. You have literally changed that bread, the starches in that bread, into a different form. And then again, here's water turning into steam, which we know is just a phase change. So that's a physical change. So burning something is a chemical change. So, ooh, there's something burning, all right. When we look at these chemical changes, we can write these in such a way as that scientists will understand what actually was going on. And so we use a chemical equation in order to do that. So in a chemical equation, an arrow indicates reactants on the left and products on the right. And so they're showing you what those are. The multiple reactants or products are separated by a plus sign, and the delta indicates heat. Okay, so you'll have something over here. Okay, so I've got two reactants that I've got a plus in between. I'll have an arrow, and then I'll have a product. Okay, and if I've heated it up, you'll see me do this and put a delta sign over that arrow a lot of times. So the plus is what you separate the formulas with. An I reacts to form products. This little symbol here is if you heat them. We also use a delta. Solid in parentheses, liquid, gas, and aqueous. That just shows what form it's in. So like if I have sodium chloride that's dissolved in water, I call that aqueous. But if I have solid sodium chloride, then that is an S. Okay, so it just tells me what forms, because sometimes in a chemical reaction, some of the reactants are only changed in form and they're not really changed to something else, and so they don't really undergo that chemical change. So in a balanced chemical reaction, it's very important that we do not violate the laws of thermodynamics, and so we cannot make or vaporize, get rid of any element in a reaction, and so we have to account for those. It's called a chemical balance or a mass balance, and so the total number of reacting atoms has to equal the total number of products that are produced. So if I have one C on this side of the arrow, I have to have one over there. If I have one over here, I have to have one over here. In this case, I've got one carbon on each side, and I've got what? 2 oxygens on each side. So as long as I've got the same number on each side of that arrow, I'm okay. So because of that, we have to balance the chemical equations. And so in order to do that, what we do is we write the equation using the formulas for the reactants and the products. We count the atoms of each element in the reactant. We use coefficients, that is the number before the molecules or elements. And then we check it at the end to make sure that we've got the correct number. Notice that if you've got something like MgCl2, that's the formula. This number right here you cannot change, okay? Because that would make it a different chemical. So you have to use the number in front of it, which is called the coefficient. So in this particular example, first they say write an equation using the correct formulas for the reactants aluminum and sulfur to form the product Al2S3. Now you could predict what this product was because from lessons long ago, remember that Al is a +3 and S is a -2, and so that gives you Al2S3, right? Okay. These are solids and they're reacting to produce a solid. So what you do is you look on the reactant side and you say I've got 1 aluminum and 1 sulfur. But on the product side I've got 2 aluminums and 3 sulfurs. So this is not balanced and this will not work. And so I've got to figure out what to do. So I'm going to use coefficients. If I've got 2 aluminums over here, I've got to have 2 over here, and I can do that with a coefficient. I've got 3 sulfurs over here, so I have to write a coefficient of 3. Then when I go back and check, I've got 2 aluminums and 3 sulfurs on the reactant side, and 2 aluminums and 3 sulfurs on the product side. And so that is balanced. Sometimes you might get a little carried away and have like, if you had like something that you could divide all of them by, like if you ended up with 4 and 6 and 2, then you would have to take those down to the least, the lowest ratio, which would be 2, 3, and 1. And of course you don't have to write the 1. Alright, so let's do one of these for real. Well, actually we got 2 to do. So state the number of atoms of each element on the reactant side and the product side for each of the following balanced equations. Alright, so this one's balanced for us. All we're doing is we're accounting for how many of each thing. So I'll do A over here. Okay, and what I do is I do what's called take an inventory. I write them as they go on both sides of the arrow. And I write them in the same order so I don't get messed up. And so I've got 4 phosphorus atoms and 6 times 12 bromines. Everybody see where I got that? It's Br2 is the molecule, so I have to multiply that by the coefficient to get the total of 12. Then I've got 4 P's over here, and 4 times 3 is 12 over there. So I'm balanced. For B, I've got Al, Fe, and O. Alright, I've got 2 Fe's and 2 aluminums and 3 oxygens. And then on the other side, I've got 2 aluminums, 2 irons, and 3 oxygens. So I'm balanced. Okay, see how that works? So let's do this one. And this time what we're going to have to do is we're going to have to balance this equation. All right, so how many iron atoms do I have over here? Let's see, in the reactant I have 3. irons and 4 oxygens and 2 hydrogens. And in the products I have 1 iron and 2 hydrogens and 1 oxygen and 2 hydrogens. Remember, I got to do them in order on the same side. All right, so I need how many irons over here? I've got 3 over here. So in order to get 3, what do I have to do? I have to multiply that by 3. And so the only way I can do that is what? Add a 3 there. Hydrogens, I need 2. I've got 2. But look, I've got 4 oxygens. The only way I can get 4 oxygens is if I multiply that whole thing by 4. I get 4 oxygens when I do that. How many hydrogens do I have now, though? Because I changed it too. 2 times 4 equals 8. So what am I going to have to do? I'm going to have to go back over there, and I'll have to say, well, I've only got 2, so I got to multiply that by 4 to get 8 over here. So I have to add a 4 there. So I have 1 mole of Fe3O4, 4 moles of hydrogen gas, 3 moles of iron, and 4 moles of water. So let's see from there's how we did. Wrote the equation, counted, used the coefficients, and so then okay, that's interesting. I think their learning check's wrong again. If you do the final confirmation, you've got 3 here and 2 here and 12 here and only 6 there. So did we do something wrong? I don't think so. That's got to be 3, doesn't it? We know that's right. And over here we have 4, and there's only 3. So that can't be right. So because you got to have 4 oxygens, and that gives us 8. And then so that has to also be 4, which gives us 8. Wow, this is like 2 times the book has been wrong on these learning checks. Okay, so anyway, this is right. Okay, we were right. It's 1, 4, 3, 4. And if y'all see I've done something wrong, you make sure and tell me, but I'm pretty sure we're right. Now, balancing equations with polyatomics. You remember that you can have ions that are 1 element, monatomic, or you can have polyatomic ions. And so we need to go and look and see how we do these. And when you first look at it, it's like, oh my word, this is going to be awful, because there's like P's and O's and everything all over. But with a polyatomic, what you do is you balance it using the polyatomic as one thing. Okay, so in this one we'd have sodium and a PO4 3-, which is what that ion is, and then magnesium and chlorine. And if you do that, it's so much easier. Okay, so in our original reactant, remember this is a coefficient, so that means we have 2 of these. So we have 2 PO4s. We have 2 times 3 is 6 sodiums. We have 3 magnesiums, and we have 3 times 2 is 6 chlorides. So on the other side we have, and I'm just going to go in order here, 3 magnesiums, 2 phosphates, 6 sodiums, and 6 chlorides. So are we balanced? Yep, we are. Okay, so that is balanced, and we balance that PO4 as a unit. It's very important. Can you do it the other way? You sure can, but it makes it really hard. So let's balance these. All right, you go ahead and you do your take inventory. All right, you put me on hold and you take your inventory. Remember, and you're going to say how many irons, how many oxygens, and how many carbons are in each of these, and then come back and we will do this. Okay, So in that first one, we had one iron, we had 2 irons and 1 iron, and we had 3 oxygens and 2 oxygens, and then we had carbon was 1 and carbon was 1. Okay, so we know that the Fe, usually you can start with the Fe if you want. Doesn't really matter. I usually, if I have something by itself, I'm going to leave it till the last, because I can always multiply that by whatever number I need to. So in the carbon dioxide, I have a 2 over here and a 3 over there. One thing I know is that for me to get them to the least common, I'm probably going to have to multiply those 2 together, if that makes sense. So what I'll do is kind of like when I was doing the ionic formula, I'll come over here, and since I've got 2 on this side, I'll multiply this one by 2. And I've got 3 on this side, so I'll multiply that one by 3. And then that changes me to having 6, so that balances those 2. And then what that's done is it's given me 4 irons over here now. And so since I only have iron by itself, I can multiply it but whatever I want to, which would be 4. And then I've got 3 carbons, and so I can multiply it by anything I want to. And so I multiply it by 3, and that gives me 3 on each side. And so 4 irons, 6, 2 times 3, 6, and 3 times 2, 6 oxygens, and 3 carbons and 3 carbons. So I've got that one. The next one was aluminum solid with iron oxide, giving me iron and aluminum oxide. And so if you have 1 on this side and 2 on that side, and then you have 1 iron and 1 iron, and oxygens, I have 1 on this side and how many? 3 on this side. Alright, and I can do that same thing again. So whichever thing has oxygen in it, I'm going to multiply that by 3, and the other one I'm going to multiply by 1. So that gives me 3 on both sides. And then irons are balanced, so I have to look at aluminum. I have 2 aluminums over here, so I multiply that one by 2, which gives me 2 aluminums. And then my irons, I had to multiply this iron oxide by 3, which changed that one. Whoops, changed that one to a 3. And so I have to multiply this one by 3 to give me 3, and that balances. Alright, the last one is aluminum, hydrogen, and this is sulfate. If you're wondering, a lot of times you can look over at the products or whatever, and if you see it in parentheses, it will remind you that that is a polyatomic. And so on this side we've got aluminum, hydrogen, and SO4. Okay, and on this side we'll have aluminum, hydrogen, and SO4. And so we've got 1, and I'm talking about originally, okay, and I've got 2 hydrogens, and I've got 1 SO4. I've got 2 aluminums, 2 hydrogens, and 3 SO4s. Okay, so I'm going to do this one like I usually do, 1 there and 3 there. So that changes me to 3 SO4s and 6 hydrogens. Okay, and I need 2 aluminums over here because I have 2 over there. So if I put a 2 there, that gives me 2. And then hydrogens, I had to multiply this one by 3 to get my sulfates, and so that gives me 6 over there, and I'm balanced. Okay, so you may be able to do this just by looking, or it's usually when you're first starting out, it's a really good idea to take inventory. Whichever way you do it though, don't forget that you need to go back and you need to check it and make sure that you're balanced, that you didn't miss something. And that's the end of section 5.3, reactants and the chemical equation. and I will see you soon on 5.4.